All right. I guess let's just start. Good afternoon, everyone. My name is Hen Sun, and I'm here with co-chair Qian Huang from Eastern Tennessee. So yeah, this session is actually trying to bring us together because we all know that AI is kind of like different. It's not like a maybe a 3-person team can just stay in the lab and figure things out. It's not gonna happen that way anymore. AI is a super like big effort of the entire community. So it's like we have to increase our like collaboration and communication, how to like share the new knowledge around more efficiently. And no one can just if one person solved some problem, other people should not spend more time on that same thing. So it's really depending on how we're gonna manage our pipeline. So the pipeline is where all these things happening. So there is no miracle there. So we just have to be more productive and more efficient. I think that's the purpose of this session. So I'm so glad that we have several very awesome talks today, and I hope that it can inspire some ideas and collaboration after this session. So yeah, welcome, and Qian, can you just introduce our first speaker here?
So our first speaker will be Ben Galsky. He is the Senior Research Software Engineer at the National Center for Supercomputing Applications at the University of Illinois. He supports a number of projects as a data management consultant, and he will discuss using MLflow for reproducible and citable machine training workflows.
Look at that. Okay. So hi, so glad to be here and be in front of a live audience. So let's get started. So yeah, I'll be talking about MLflow and give you some background on what that is, and then take you through a short demonstration. We'll see how that goes. So who am I? So I started out as an IT consultant in industry, and 6 years ago moved over into research computing at NCSA. And NCSA at the University of Illinois is both the home of the web browser and where the HAL 9000 was supposed to have been developed in 1999. So I work on a number of different projects in the software directorate. I like to think of myself as IT consultant for science. And so I get to work in high energy physics and material science and chemistry. Oddly enough, I don't do very much in earth science, but I love coming to this conference, but that's a whole other story. And one of the things that a colleague and I have been working on is a data management consultancy. So like trying to come into grants before as they're being written, contribute a data management plan and try and get ourselves written in to help with data management. And we see models as part of that. So here are 3 challenges I see. I'm sure we all have our own 3 challenges in machine learning and research. So one is just productivity and training, reproducibility, good luck with that, and then being able to like cite and distribute models. And so, not surprisingly, I'm going to talk about MLflow as a possible solution to some of these problems. So it's an open source platform for the complete machine learning lifecycle. That's what they call it. It was developed initially by Databricks, who have commercialized Spark, but it's a very popular open source system. So here's kind of what it is. So one of the things, so first off, it's open source. And one of the things I really like about it is it's incredibly lightweight. It doesn't require you to adopt some other workflow for your machine learning training. It doesn't require you to use specific libraries or specific packages. It's a very lightweight library that you bring into either Python or R. I think it also might support some other languages. And it runs exactly the same way on your laptop up to an HPC. And it can be useful for just your own personal use, but it's also set up to support like a larger group. So there are 3 big components to it. There's tracking, which records your training runs and all the hyperparameters. There's projects, which is really a very interesting, just like a format for packaging up reproducible training runs. And we're actually applying it at NCSA for some like Monte Carlo simulations and other things, because it's just a very useful way of packaging up workflows. And then models, which allows you to version and serve models in different formats, and it makes it very easy for people to consume your models. We'll talk about each of these in more detail. So tracking. So it has these concepts. So there's like parameters, which are like your hyperparameters that go into your code. It'll track every time you do a training run, what were the hyperparameters that went into it? And then as your training run goes about its business, it can report metrics back, loss functions, other things. These all get recorded into a database. Artifacts, so just whatever files you might produce, including models, but it's also quite interesting to take all the plots that you might be making as part of your training run and store them all in there. And I'll show you in a little bit just how fun that is. Keeping track of the source code and like the Git SHA of your source code. And so really the idea is that as you're doing training, you're fiddling around with the code, you're fiddling around with your hyperparameters, it's getting better and better, and all of a sudden, oh, now it's not fitting as well. Like, what did I do? And so the point of the tracking server is you can always go back to any of your previous training runs and see exactly what went into that. And then you can tag them with like some notes and different information. So concretely, well, actually not very concretely, it's just a cartoon, but it looks like this. There's the MLflow tracking server, which is just a Flask server that can run either on your laptop or hosted somewhere. And it has a REST interface, Python, Java is also supported, and R. And so you just log stuff to the tracking server, and then there's a UI and an API that you can go in and query it later. So here's what it looks like just to instrument your code. So it's with some Python code. Yeah, you tell it that you're using MLflow, and then you just log parameters, do your training, log your metrics, and then it has some really nice helper functions. You can just take a TensorFlow model. It knows all about TensorFlow. It can interrogate it and publish it, and then you'll see how there's a bunch of interesting information that comes out. So that's tracking. The other thing is projects. So this is a specification that most importantly has, it has lots of things in it, but one of the things I think is important is your dependency environment. And so if you're using MLflow projects, every time you run, it checks to see if you've changed your dependencies and builds a virtual environment. So, kind of if you follow the flow, you can guarantee that it was run inside a virtual environment that was created from this particular spec. And so you can just hand that spec to anybody else. And in theory, they can do your exact same training run. And you can run it on your laptop, or it has built in some backends for remote execution, Docker and Kubernetes. And because I work at NCSA, okay, I'll get back to that later. So because I work at NCSA, we've worked on a Slurm backend. If you have access to an HPC, you can spin up hundreds of jobs, and they'll all report back to the tracking server. So, concepts are, really it's just like a standard for a GitHub repository. There's a file that goes in there that describes how you run the thing, defines all the dependencies, and then you can do it, make it easy to run different things. So here's an example of a project. So this is, in this little box, is what the ML project file looks like. And so you can have multiple entry points. So maybe you've got a data prep step that you want to keep track of, and training, validation, different things. And then you pull out your hyperparameters, because MLflow would want to know about that. And then it just can run any arbitrary command. Here, usually it's running a Python program, and then it's all nicely packaged up. And if you want to run it, you just say MLflow run. And if you want to be really precise, you can just tell it to run a GitHub repo. And so then you're guaranteed you have reproducibility. And then here's the Slurm backend. So you just say MLflow run backend Slurm, and then you give it a config file that just has just a few bits of information for your Slurm job. And so it makes it very easy. You just MLflow run locally on your laptop. This looks pretty good. -- backend Slurm, and now you can scale it up onto a supercomputer. And then models. So, at the end of everything, you would want to be able to publish a model, share it with your colleagues. But one of the things that I don't think we do as much in academia, but in industry, models are never done. So they're always evolving. And so the MLflow model repository allows you to version them and say, so this run produced this model. If you want to use that, great. If you want to use my latest and greatest, I'll just call it production. And so anyone can come along and just grab your latest production model. Or if you've published a paper, you can give it a very specific tag, and then you're guaranteed that anyone who comes back and wants to reproduce the results from your paper will find that model. MLflow supports serving models. I can show you some examples of that, but either just simple, download it and run it in against a Pandas data frame, or there's backends for Triton, the NVIDIA GPU server, and other sort of inference engines. So at its core, again, it's just a standard, like a directory format and some file formats that make it easy to publish a model and make it reproducible. The model, when you publish it, also has all the dependencies in there. So anyone who wants to grab your model, they go where the the pickled files or the the model binaries are stored, and then they also know exactly what dependencies and which versions to install. And there's some nice APIs and all that kind of stuff. So here's an example. And so what they've done is they have these flavors. And so you can just say, model predict, and it knows which flavor it is. And so, prediction with TensorFlow is different than PyTorch, and that wraps all that. And so it's really a very nice library. And so I've worked on a couple of projects where we just like the ML model and being able to pickle your models and make it easy to run them. And we don't want the rest of the stuff. And so each of these components are actually quite useful on their own. Demo time. Okay. So Zihang suggested that I start with oh, here we go. These ML, they are, what are they? It's like it's a textbook, some example textbook for learning, machine learning and earth science. And so I've started with the sea ice prediction model. And so I just wanted to show, here's some of this, what I had to do in order to instrument this Jupyter notebook. And so one of the things I did is because part of the benefit of MLflow is being able to surface your hyperparameters and keep track of them. I kind of went through the notebook and found what looked like the hyperparameters and put them in this one cell here at the top. And this tag parameters will come in handy in a bit. And then usually make a variable like a Boolean, use MLflow, because maybe you don't want to mess with it while you're doing some serious development. So then, conditional that says if you're not using MLflow, don't do all this stuff. But otherwise, all I do is I set the tracking server URL to a instance that I've set up at NCSA, which doesn't have authentication on it. And if you want to make a note of this, you're free to use this for the rest of the week if you want to try out MLflow and see what you think. And then just saying start the run, and I'm logging one of my parameters, and I'm telling it that it's using Keras models, and it actually goes in and instruments Keras and logs a bunch of stuff on my behalf back at Basecamp. So then pretty much everything else is exactly the same. Scroll, 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 scroll. I've taken the plots, and at the end of them, if I'm using MLflow, I take the graphic, the image file, and shove it back into the run as a PNG file. So let's see what this actually looks like. Here we go. So here I am back at ecip.ml.software.ncsa. whatever it is, it's in the slide deck. And so here are some runs that I've done previously. And it comes up with great names for them. And you can see that, with different hyperparameters, let's see, so here's worried stork. And so I can see, okay, wait, parameters. So batch size was 32. And a lot of this logging was done by automatically because it knew it was a Keras model, so it pulled a lot of this out of there. what was my optimizer, Atom W. And then I can see metrics. So here's my loss function. And I can click on it and see over the epochs how that, how that converged. And here's my model, and as promised, so here's the model already pickled up here, and here's an example. So if we want to use this model, I can download it from my repository and then just say loaded model.predict. And so you can also, and I didn't really understand this notebook well enough to figure out how to do this, you can provide schemas for your model so everyone knows like what parameters go into it. Let's see, also I've taken here my PNGs and I've uploaded all of those. So all that stuff is in there. I can go back, let's see, actually we go back to my experiments. I can see all the runs. I can sort by loss. I can see the different things. I can also do a chart view where I could have had it. I thought this was already done. So you can see, by run, you can look at that. You can do, there's like all sorts of charting. I'm not going to go into that. But what I wanted to show you is, so everyone loves notebooks. They're great for doing all your development and debugging, but it's really not great for reproducibility and not great for running a bunch of batch processes. So what I did is I'm not sure how many people are familiar with Papermill, which is a Python library for running Jupyter notebooks like batch. And so what I've done is I've taken the notebook and added that tag parameters on the first cell that had all those hyperparameters in there. And if I say papermill-p, I can override those variables with things from my run here. And so here I've defined my project. I've got my Python environment that has everything pinned down. So if I can give people this, they can run it again. And then if my terminal is still working, yes, it is. Oops. No, wrong project, ML. Perfect. So here's just a command line. So I'm telling it the tracking URI for my MLflow, it just picks up from the environment variable. And I say MLflow run -p, and here I'm setting the number of epochs I want. I can, all my hyperparameters are now exposed here. And then just run it. It'll go off, report all this stuff back to the MLflow tracking server, which is great. But if I want to do a hyperparameter sweep, I can, run this with Python. There's a Python SDK to run MLflow runs, or make a big batch script, run hundreds of them, maybe on my HPC, go home for the night, come in the next morning, and you can now interact with all of your runs and sort by loss function. You can do all sorts of different things, and all the models are there. So to summarize, the 3 challenges in ML research, why I think MLflow helps us with that. So for training productivity, you can really track the impact of hyperparameter and code changes. You can really run hyperparameter sweeps quite easily and make it easy to switch from desktop to supercomputer. For reproducibility, we've got the enforced use of reproducible runtime environments, and you can trace your model back to a specific run. So I know exactly what hyperparameters went into this model, and then I can publish this model to the repository, and then my borders covering, you can version them. So skip this. I want to give thanks to Corey Zumar, who is the chief maintainer of MLflow, who I got some of these images and some ideas from for the presentation. And find out more, here's the link to the tracking server. You can go and hack around on the tracking server. Here's the link to the MLflow Slurm plugin, and a link to my fork here. Thank you very much. Can we do questions now, or? We have 3 minutes for questions. Sure. Yes.
So is the MLflow server something that is simple enough that you're able to like spin it up locally if you're doing just local production and then turn it off when you need to turn it off and so on? Or is it something that needs to be persisted?
If you want to, if you want to share it with your friends, you'd want something more, but it's just a Flash server. You do pip install MLflow serve, done. And if you have access to a Kubernetes cluster, we have a Helm chart for deploying it. So, and can definitely help people get started on it because I'm a bit of a Pied Piper of MLflow.
Besides the example that you showed, are you aware of any other examples in earth science that we can look at, or are you proposing this as like, let's start now?
As far as I know, let's start now, but there is a ML Ops talk later this afternoon, so it could be that it's happening, but yes.
So it's MLflow based in Python, and you're saying that it can be working with like R and other. So basically, people need to use Python to track R to do that.
So the MLflow server is REST based.
Okay.
And so there are library R packages that we call them, R packages
So they have a wrapper in R to.
that just talk to the REST interface. There's no Python in your code at all.
All right.
All right, thank you.
Thank you. So our second speaker will be our ISA fellow, Mike Mahoney. Mike is a PhD student at the State University of New York College of Environmental Science and Forestry, focusing on predictive model and visualization with a focus on natural systems. Mike, floor is yours. Go ahead.
Thank you. Everyone sees a present button. The other, I think that just opened in Edge. Let me try opening that in Chrome. Here. Yeah. There we go. And I need to share it for the folks online. Good. All right. Yeah, thanks. Hi, everyone. I'm excited to talk about, mapping shrublands across New York State. For a bit of context, so this is going to be me telling the story of a paper and a book chapter. And specifically, it's a book chapter in a book that was led by Jensen. Where is that other Chrome browser? I'm trying to change the screen share. Sorry, excuse me 1 second as I try and find that. But if you are interested in the specifics of how all of this got together, I'm just gonna not find it. If you are interested in the specifics of like how this all came together, that book chapter is available entirely on GitHub in Quarto, which is successor to R Markdown. So the actual code and data and everything is embedded in the book chapter that then renders out to PDF. But so I'm gonna be telling the story around that, which to start off, as Chen mentioned, so in addition to being a community fellow this year with ESIP's Information Technology and Interoperability Group, last year with the Machine Learning Group, I'm also currently a PhD candidate working on using predictive models to help address environmental challenges. And specifically, I work with this group. It's the Climate and Applied Forest Research Institute, helping New York State track its, excuse me. There we go. helping New York State track its forest resources available as it tries to hit net zero carbon over time. So in 2019, New York State passed its Climate Leadership and Community Protection Act, which established that by 2050, the state's aiming to reduce total greenhouse gas emissions by 85%. That remaining 15% is things that are considered to be irreducible emissions, which will hopefully be offset by increased sequestration in lands and forests across the state. Now, if you have a goal of offsetting 15% of your emissions, you have to be able to actually track that, and you have to be able to actually manage to promote more sequestration in lands and forests. So what our group does is we help the state try and identify current carbon pools as they exist now throughout the state, to try and measure how that's changed going back to about 1990, to forecast how that will change in the future, but also to identify good areas for management that if you reforest, if you afforest, so plant for the first time, if you conserve, so just keep the land from being converted for other purposes, that you can then use that land to sequester more carbon than's currently being stored. And to that end, we were looking at trying to identify shrublands across the state as areas that would make for good targets for that type of conservation work. That's the sort of thing that sounds like it should be easy. Specifically, if you are familiar with land cover mapping, there's a lot of really high quality land cover products that track shrublands. Specifically, if you use NLCD or LCMAP, which takes LCD classes and makes annual classifications from its surfaces, shrubland is one of their top categories that they track. But there's some challenges with shrubland that makes it so that these national products don't really do a good job on the East Coast of identifying shrubs. And this is not meant to be a critique of NLCD or LCMAP. They are fantastic, irreplaceable products. It's just that there's a few issues with shrubland that made them not really useful for our purposes. Specifically, I keep saying the word shrubland, and if you're from the West Coast, you're probably thinking of something that looks like this. Shrublands in a huge chunk of this country are these large, relatively open, so few woody trees, persistent ecosystems that have unique community compositions. If you're in the Western states, that's what this looks like. Out here in the East Coast, we don't really have that type of persistent shrubland. We have short forests. And having one classification cover both of these types of forests makes it really difficult for these models to actually pick up on eastern shrublands. In particular, identifying this type of shrubland is hard for these models because they also just don't have a lot of examples to work from when they're training. So for instance, this is a map of all of the shrubland in NLCD's 2019 product across New York State. If you're sitting at the back of the room and you can't really see what's going on here, that's the point. There's not very much to work with. Our best estimate is that for New York, it's about 2.5% of the state that's actually these shrublands. Add in that those shrublands are ephemeral, eventually our short forests just become forests. And it's really difficult for these products to actually capture these areas while they exist. Last but not least, because our shrublands are just short forests, it's really difficult to identify them based on imagery alone. So as an example, this here is, the blue pixels are areas that NLCD called shrubland in 2019. If I take away the blue and you blink so you can't see the outline anymore, it's really, really hard to see where those dividing lines were. Spectrally and based off imagery, they look pretty much the same. They're made up of the same trees, just shorter. And so from the data that's available for these national classifiers, it can be really, really difficult to find these areas. Now, an advantage that we have versus the national products is that I only care about New York State. I have no need to address the rest of the country, which means that I'm able to use things other than just satellite imagery in order to make it so that we're able to better capture this type of ecosystem. Specifically, because our shrublands are just short forests, we were able to take advantage of the LiDAR data that we have across New York State. So this here is, as of 2020, the LiDAR that was available across New York State. And we could use that to supplement our Landsat data and other imagery in order to actually make our models better at capturing this ecosystem. Now, the issue is that, as you can see, we don't have LiDAR for everywhere. Even now, 3 years later, we've got a lot more LiDAR than this, but we still don't have LiDAR for the entire state, flown since 2010. And at the same time, each one of these colors is a different year that the data was acquired. If we care about capturing this ephemeral shrubland while it exists, LiDAR does not get us there because we don't have it for the entire state each year. What we could do instead is use this to actually help us train our models in the first place by using it to classify and find shrubland when the LiDAR was taken to actually label our training data for our models. So we took LCMAP's shrubland prediction, or LCMAP's classifications, and looking at just the vegetation pixels from LCMAP, we used the LiDAR data to classify it as either shrubland or not shrubland. Basically, if in the LiDAR a pixel was taller than 1 meter, so not grass, shorter than 5 meters, not a forest, would call it shrubland. It's not a perfect classification. In particular, New York State's biggest crops are apples and grapes, and orchards and vineyards aren't great targets for reforestation. It got us most of the way there. Based off of our accuracy assessments, it was good enough for us to start actually labeling our data with. And so we took those labels, we took a bunch of data that we do have statewide for every single year. So things like Landsat imagery, things like elevation data, temperature, precipitation, and we used that to actually fit a handful of models. So we were using random forest like GBM, neural nets, and then a logistic regression to combine those into one final camera-ready set of predictions. And that camera-ready set of predictions wound up looking like this. Now, these dark blue areas are areas that we don't think are shrubs. The brown areas are areas that are more likely to be shrubs. And when we saw this map, we were pretty happy with how things had turned out. For anyone who's not familiar with New York State's geography, that really dark blue area up in the northern section is the Adirondack State Park. It's the largest state-owned protected area in the lower 48. It's been continuously forested for just over like 130 years now. And as a result, it really doesn't have much of this shrubby area in it. So we were happy to see that spatial pattern. Similarly, all those northern areas that are brown, especially along Lake Champlain here on this edge, those are areas that we know have a lot of farmland being abandoned that's returning to forest. So spatially, this approach seems to do a lot better than what the national products are able to give us. And when we started looking into actual accuracy, we were seeing also pretty good patterns here. So these distributions, the blue is non-shrubland pixels, the brown is shrubland pixels. And as you can see, we're getting really good class separation. Generally speaking, areas that are shrubland, high probabilities, areas that aren't. Winds up being the AUC for this model is something like 0.9, which means it's doing a pretty good job at actually classifying these pixels. The only challenge is that, as I said earlier, there's really not a lot of shrubland in New York State. Again, about 97.5% of the state isn't shrubland, which winds up meaning that even though this model is doing a really good job at classifying these pixels, our precision winds up being pretty bad. Because if we have, for instance, a model that's right 90% of the time, and you've got 1 shrub pixel and 10 million non-shrub pixels, if your model's right 90% of the time, you're gonna have 1 million false positives. So what we wind up having to do as we actually operationalize this model and as we're working with the state to identify shrubland areas is we wind up having to use a really, really high threshold, usually about 95% probability, to actually classify areas that we think are shrubland. And that winds up getting us to about 50% chance of whether or not the pixel is actually shrubland. An interesting thing here is that you can see we drop off as you actually get towards 100% chance, because you start getting into areas that were misclassified by LCMAP originally. That tends to be the tops of buildings or something that the national products thought were vegetation. So things really fall off once you get outside our original training data. But being able to use these high thresholds has been really useful for us because we're also not necessarily interested in individual patches of shrubland when we're trying to target management. As we're talking about areas that the state should work on conserving, should work on planting in, we want to look at larger agglomerations of shrubland. And so having a large area with high probabilities of shrubland is a really good indicator for our management activity. So this model's already been really helpful for us and our partners at the state in identifying those areas. So if you are interested in this project, I want to do a quick plug that in addition to the book chapter, AI for Shrubland Identification and Mapping, which is both available online and also on GitHub as the Quarto document, we also had a paper on this in the International Journal of Remote Sensing last year, if you're interested in more. And with that, just want to say thanks. If you want, you can find me online. I'm at mm218.dev or Mike Mahoney 218 on everything. Thanks.
So, sorry, I know you probably said at the beginning, but the objective of refining this classification is because there's a reforestation effort in these areas to try to bring this shrubland and actually make it.
Yeah, so especially in like the New York context, when we're talking shrubland, we have very, very like tiny amounts of land that are actually persistent shrublands. It's almost entirely areas that are already naturally regenerating. So yeah, the interest is in either if you can conserve those and let natural regeneration take that back to a full forest,
Right, okay.
or if it's an area that you're concerned about, you can actually actively plant
Right.
for additional carbon sequestration. There's also a lot of other interest in sides here where in the Northeast, generally speaking, all of this land at one point was clear cut and farmed, which means that kind of all of the forest in this area has a certain max age to it. At the same time, most of the forests in this area come about around the Great Depression when a lot of farms went bust and the state took the land because they went default on their taxes. So if you have a state forest, that's almost always how that state forest originated around here. So we also, generally speaking, have a minimum age for all of our forest. So that's part of the reason that it's so rare here. So the state is interested in having more of it because there's animals like turkeys and things like that, which enjoy shrublands much more than tall trees that they can't get up in.
Sure. Okay. Okay, cool. Thank you.
I'm here because of the carbon.
Right.
I guess two questions. One for the session about workflow. So what's your workflow looks like? Are you taking the real-time or near real-time Landsat data, feeding into that? And I know they are also, Maryland produce analysis-ready Landsat data. Are you using that? And the other one question is, I know Esri and Impact Observatory is partnered up and then doing a 10-meter resolution land use and cover maps every year. So have you compared your output with New York State from that specific product? Because that higher resolution probably have more benefits for that.
So we haven't done, to do the second question first, the 10-meter product, we haven't done a rigorous comparison between our product and the 10-meter. Our spot checks indicated that it wasn't going to be very useful for us. So we kind of abandoned looking at it after that. Yeah, so basically, compared to LCMAP MLCD, this product does seem to be doing better at capturing this one specific cover type. Compared to that one, I'd imagine it's similar. I imagine that you fall into similar issues because that's also a global product, right? So I imagine you run into similar issues with having too many different definitions of shrubland collapsed into the same category, but I can't say that for certain. For the first one, for the workflow question, yeah, we're consuming, so at an annual basis is how often we update these products, because we're basically using indices for the entire summer of imagery. So the average of the meteoid composite of these images across the entire growing season when leaves are out. So we consume the analysis-ready Landsat data, do our own post-processing to harmonize it across years, and then run that through. We've got a standard, this is primarily R-based, so it's a targets job, and that targets job consumes those indices and winds up outputting these predicted maps. And yeah, if you're interested in like the modeling specifics, the Quarto document goes deep into how we built out the neural net part of the ensemble.
I was kind of interested in what you used for ground truthing. Was that using the LiDAR, or do you actually have ground plots?
So we don't have ground plots. The best that we were able to do on the budget available to us was we have, I believe it's 2,000 images that were assessed through like high resolution ortho imagery. Now, that's one of those things that it is still difficult to tell how tall a tree is from an aerial photo, even if it's not a satellite photo. So it winds up being, I think about a third of those images get marked as not sure. But off the ones that we can tell is how we're comparing against LCD, LCMAP for those accuracy comparisons that we do. Yeah, it's similar to how I believe LCMAP's primary like verification, because they also use, I believe, the NRCS plots. Yeah, I think.
What's the source of the LiDAR data?
So the LiDAR data is primarily from the USGS 3D elevation program. So leaf-off LiDAR that they're using for DEMs primarily.
Got it. Yeah. And then second, you had mentioned something about your false positives in like specific areas where there's like, yeah, can you just explain that again? Like, where were you seeing false positives, and like, how do you deal with that scenario?
Yeah. So the issue is primarily that, as you can see, based off like these two distributions, I mean, it gets a little muddy on the right there, but both of the distributions have tails pretty much to both extremes of the probabilities that we can predict, which if this was like, a 50-50 class split would mean that we have about as many true negatives, or rather about as many false positives as false negatives. Instead, because shrubland is so rare, even though it's roughly the same rate of false positives, because there are so many more true negatives, that rate applied to the much larger number of actual negatives means that that can really wind up swamping the signal of, even if we classified every single shrubland pixel correctly, that's 2.5% of the state. If it's, again, about a 10% error rate for the false positives, 10% of 97.5% of the state means that we wind up having like 4 times as many false positives, just because it's such a rare class in the first place. So yeah, it's the distinction between like precision versus specificity. All right, awesome. Thank you.
Our next speaker is Andrew Huang, and he's a software engineer in Anaconda, and he is an atmospheric scientist, a Python developer, and an open source contributor. And today he will discuss easy exploration and ML model tuning with HVPlot.
Tab really quick. Okay. Full screen. Guess I don't know. Oh, sorry. Does anyone know how to full screen this? Somewhere. Guess it doesn't really matter. So to start out, who here uses Python? That's great. And who here uses Matplotlib? Awesome. So today I'll show you another way to plot, and that's using HVPlot. Another question is, who uses pandas or Xarray? Great. So HVPlot plugs into Xarray or pandas really easily. Whether it's GeoPandas or Xarray, it all works. So these are my goals for today, is to demo HVPlot's ease of use and features, and how you can use HVPlot for ML. And along the way, share applicable pro tips for data workflows. So we'll be plotting a track of Hurricane Katrina, plotting a climatology of hurricanes, as well as creating a correlation heat map, and then comparing the observation or the verification data with predicted data using HVPlot. So the first thing we're going to do is download the data from the International Best Track Archive for Climate. It contains records of tropical cyclones since 1980 and includes the coordinates, intensity, wind speed, and central pressure, and more. Then we're just going to read the data with pandas. And we can remove the second row since it's just an R header row and then fix the data type. So here you can see some of the data columns. So you can see season is the year and like sub-basin and basin like South Pacific or something. And then we're just going to export to Parquet. This is one of the pro tips. If you're reading CSV, it's very inefficient to always load it back in. Parquet is like a chunked, I guess, file format, so it's much more efficient and it's accessible by many tools. The next step is we're just going to query for Hurricane Katrina using this simple pandas query. So we're just going to set name equals Katrina and season equals 2005. If you know SQL, you can also do it with DuckDB and then convert back to pandas with fetch.df. And then here's what you do usually in Xarray or pandas. When you have the data, you usually type plot. But instead of plot, you can just replace it with hvplot and you get an interactive plot. So you can specify the type of plot and then you specify the X and Y and you can color it by the category. And then another pro tip is if you set tiles equals true, you can get a base map for spatial context. And then with matplotlib, you would have to call methods to set the title or color bar. But in hvplot, it's really easy. You just specify C labels equals the name of your color bar label or title equals that, all in one call. And you got this interactive plot where you can zoom in, zoom out, and pan. So here, if I zoom in, the details would, I guess, update. And you can actually see that Hurricane Katrina made landfall around August 29 and was a Category 3 hurricane when it made landfall in New Orleans. But we don't have to just plot Hurricane Katrina. hvplot allows you to explore your data in many different ways. For example, if you want points instead of lines, you can just use points, and you can get group by to get a drop-down menu for each storm. So if this server did not sleep, awesome, it works. You can basically see like all the hurricanes in 2005 and explore them one by one. And here we can see if we zoom in, zoom out, you can see a better picture. So this was around here. So with hvplot, all you needed to do was specify a group by, so you're not overwhelmed with the data. But we don't even have to just plot one track at a time. What if we plot all the tracks since 1980? It becomes an overplotted mess. You could theoretically explore it, but it's hard to extract any details. Other than that, like the more northern latitudes are lower categories. I think it turns into an extra tropical cyclone by then. So what we can do is instead use rasterize equals true. So this can plot billions of points efficiently, all on your laptop. And this is actually running on Hugging Face. So even on Hugging Face, the free tier, it was able to plot a lot of these points. And it uses the package data shader under the hood to aggregate point data into pixels. And then we tell it how we want to aggregate it, which is the max. So the max category, like which hurricane had the highest category. And we can easily change like the color limits or color map by setting more keyword arguments. And here you can see a lot of Category 5 hurricanes in the West Pacific. And yeah, so you can plot a lot of points. And you can also update the X sampling and Y sampling so it can be more cohesive rather than just like sparse data. So here's a midpoint summary of what I talked about so far is that you can use hvplot for interactive plots with hover, pan, zoom capabilities, and you can get a base map overlay to get spatial context immediately without much work, just specifying tiles equals true. And then if you have like groups of data, you can use group by. So like if you have a column name called like the hurricane name, you can group by the names and visit each hurricane separately. And you can specify multiple column names in group by. So it doesn't have to only be one widget that you control. And then you can use rasterize equals true to plot billions of data points efficiently. And if you want to build a dashboard, it's possible with Panel. So check out this customization page. If I have time at the end, I'll show it. And for all the configurable options. Now we're going to move on to how I use hvplot for ML. So some motivation is that El Nino events generally suppress Atlantic hurricane activity. So let's test this hypothesis using hvplot and scikit-learn. The first step is subsetting the hurricane season in the Atlantic basin. So if the hurricane season is from June 1st to November 30th, we just select isotime.datetime.month between, and we can verify whether this query worked by just visualizing it, just by setting keywords again. And here we can see that all the Atlantic hurricanes were subset. And then we can compute the number of unique names or number of unique hurricanes per season. So if you're not familiar with hurricanes, only one per season, each name is unique. So it's in alphabetical order. And if you use between to filter between two values, it's easier than writing greater than or less than in two queries, I guess. So you can just use that. And then here you can see that if I zoom out a little, maybe. In 2005, there were 26 named hurricanes, and in 2020, there were 28. So here you can see hvplot allows you to zoom in or hover and basically explore each data point easily. And then the next step, since we're predicting the number of hurricanes, we're just going to use some ocean data temperatures to predict the upcoming season's hurricane count. And another pro tip is you can read URLs directly with pandas. You don't have to download the data first. You can just load it. The downside to this is that you have to, if you rerun the cell or rerun the script, you have to re-download it every time, which can lead to latency issues. But if it's a small file, it's really easy to get the latest data just by reading from URL. And if you specify parse dates equals true, it'll convert it to a datetime index, which you can do other stuff with. So here you can see we get the depth at average temperatures up from 0 to 300 meters, warm water volume, and the wind. Let's see, I think I skipped one. So we're just going to subset the predictors from January to May, because previously I mentioned that the hurricane season runs from June to November. So to predict the upcoming season, we just need to subset the data prior to that. And if we use lambdas here, it's easier to just assign columns instead of writing it on a separate line. This should say one line assignments. And we're just going to join the data frames on the year. So you have the unique counts as one on the left side and all the Nino variables on the right. And we're going to check out the correlation scores. Again, here we use hvplot. We just specify the type of plot we want, which is the heat map, and specify the X and Y, and we get this nice heat map as well as the color. So here you can see that the correlation for winds are pretty high, up to like 0.6. And the Nino indices are not very correlated. They're much less correlated than the raw variables, like the temperatures at 300 meters. So what we're going to do next is just subset these high correlation features And so we're going to convert each of the month row as individual predictor columns. And another pro tip is if you want specific prefixes, rather than typing out each individual column name, you can use regex to select all the names. So like instead of typing T300 East M4 or T300 East Annam, you can just use T300 to select all the columns. And then we're just going to create some ML helper functions, which splits the data into training and validation, and then fits the model and makes a prediction. And then we also have a separate score function to calculate the correlation and root mean square error. And run a linear regression. So we're just going to split the data set into X and Y, and then run k-fold for reliability and preventing overfitting. And you can see just by using a simple linear regression and using those feature selected variables, we get a pretty high correlation. So like 0.8, 0.9, and pretty decent root mean square error. And you might be wondering, what if we don't select the features using that HV-plot to analyze it? Well, we can try rerun it again without feature selection. So the top plot is with the feature selection, and the bottom plot is without the feature selection. And you can see that the scores are generally lower than the scores with the feature selection. Like the highest for non-feature selection is 0.79, but the highest in feature selection is 0.91. So you can see that manually selecting your features, at least for linear regression, is helpful because it reduces the noise. So here are some ideas if you want to play with this, is using different models. Like you can also just use the same workflow for deep learning models, or even use different predictors like NAO or something. And then you can also engineer your own features, like using the previous year's count. If the previous year had low hurricane count, would the next year's hurricane count increase? And feel free to share your results in the community. We have a very vibrant community in Discourse. So yeah, if you want to check out this, the code, it's all available in this QR code. And yeah, keep in touch. I would love to hear your work. Any questions? Oh yeah. Yep. How do I do that? Okay, yeah.
Could you summarize the difference between HVplot and matplotlib?
Yeah, so HVplot uses matplotlib or Bokeh in the backend. And HVplot is actually a even higher level than, let's see, HVplot docs, I think. It's built upon HoloView. So here's a graphic. So it uses, it can even use Plotly. So HoloViews is like the mid ground, and HVplot's like the high ground, or like the highest level. And there's so much things you can plot with HVplot. Like if we look at the reference gallery, it's not just heat maps. You can get box plots easily just by using .box. Like it's really, really strong or very powerful. And violin plots. And if you work with shape files, it also works. Just specify HVplot geo equals true. There's so much things you can do with HVplot. Vector fields as well. And yeah.
Similar question, but comparison to Plotly.
Yep. So HVplot, in my opinion, works better than Plotly, but I also maintain HoloView. But no, prior to joining Anaconda, I was an avid user of HoloViews and GeoViews and this whole ecosystem. I personally haven't used Plotly as much, but I feel like HVplot plugs into Xarray and Pandas a lot better. I could be wrong since I'm not a Plotly user. Also, all of HVplot and Panel are open source. I think part of Plotly is not. Maybe I could be wrong. So yeah. But yeah, you can do a lot with HVplot on top of HoloView. and another things I want to highlight is HoloViews you can use with streaming data, or like you can select data and let's see, let me try to find a good example of ideas. HoloViews. See if this loads fast enough. So like you can link two plots easily together. Like if you want to select a point on the map, you can get a time series, or if you want to get a violin plot of like all the latitudes, like you can see over the ocean that the distribution is pretty small, but over land it's much larger. So yeah, HoloViews and HVPlot makes not only exploring data really easy, but you can build advanced streaming functions. Like you can interact with it easily. Let's see, like here, if you want to only select specific points, that's also possible. Like here, like if you want to select data only for that region, you can do that as well. There's a lot of examples here. And one final thing I want to mention is panel is if you want to build dashboards, it's really easy to build dashboards on top of your HVPlot code. I don't think, oh, it actually works. But yeah, because usually it requires a server to run behind. But yeah, you can like explore your data any way you like. And here's the code. And it's really simple, right? You can bind your plot with widgets. So your widgets are X, Y, and N clusters, and then bind the callback. And yeah. So any other questions? Yes.
So with increasing level of abstraction in Blast code, are there trade-offs in how you can customize? I mean, like the rasterize example, how well can you say this is the size of the pixel, this is the criteria for including it, if there's partial overlap of the point, it's right on the border.
So data shader allows you to control a lot, or HoloViews, I can show you. There's, actually, let me show you HVPlot customization option. So you can also dig down all the way to the backend level with hooks, but usually you don't need to because HVPlot supports almost every option in my opinion. So like if you want to change the size or marker, it's all available here, like S here, size of marker. And if you want to use like rasterize, you can control like the X sampling and Y sampling. So there's a lot of fine-grained control as well as HoloViews hooks. If you really need to drop down to like the matplotlib level, you can also use hooks, like write down, like plot.handles x-axis, change the label color to red. I think this is bokeh, but you can do that with MPL as well. So it's very customizable. Okay, thank you.
Last but not least, our last speaker will be Ziheng Sun. He's also the chair of the ESIP Machine Learning Cluster, and he's a principal investigator at the Center for Spatial Information Science and Systems, and a research assistant professor at the Department of Geography and Information Science at George Mason University. So he will talk about PyGeoWaver, connecting Earth AI workflows in Python.
Yeah, I'm gonna use my own laptop, so. Oh, host disabled the. Yeah. Right. It's not loading. Oh, okay. Anyway, Probably I need to share the entire screen. Okay. Yeah. Hello, everyone. So this is like just a short presentation, and the main purpose is give you some like demo, and hopefully you can try some hands-on experiences. So yeah, we actually have a problem with us AI workflows right now. It's like we have seen thousands of papers already published in the past 5 years, and very few of them made into the production, unfortunately. And we have thinking about the problem for many time, like for a long time, and we figured out that some of those like it's actually they did most of the experiment on the prototype data set, and AI is actually have a lot of challenges. Every time you are talking about I want to use AI to this task, you actually automatically bring like dozens of challenges into your task. So it's not always suitable for your work. And even the paper is published, they only tells you one possibility. It's not there are numerous possibilities in the real world, but it only gives you one instance. Like in this scenario, it works, but it doesn't mean that it works in the real world. So that's part of the why it's so hard to make the AI production ready right now. So we figured out that it's really limited resources, right? So every small groups, they only have like limited time to try one or a few possibilities by themselves. If you really want to make it work, you have to collaborate with everyone. So what's the real bottleneck problem? So we started the industry. Industry is super successful in the AI application, right? So we started that actually there is several bottlenecks. It's like the AI workflow is normally the full stack. There is a lot of like the model is actually tip of the iceberg. There are a lot of work done below the surface you haven't seen. Most of the work is in the data preparation and post-processing. So why they are so robust, and they have a very the pipeline is working for everyone, and because there is some issues happens, they will just like 1,000 people will show up and fix them. Because all this source code, the code base is shared and open and accessible by all the engineers in the company. But in the earth science community, and if there is something goes wrong, what we do is like send an email, and that's it. So yeah, it's not one or two persons fault. It's actually the entire scientific community is like, the settings is not suitable to do this kind of work. And what we should do is like make AI workflows more shareable. And if anybody just get your work, and they will instantly understand what you're doing and can continue based on your progress, can continue your experiment or continue to push out the workflow, just like what they did in the industry. That's how we can make our workflow more production. So we have this like a low productivity issues because we lack of full stack workflow. Because in the industry, the people in that company has like access to all the code base, but we probably when we're sharing a part of it. And how did you get the AI ready data or the training data, where it came from, what process you used, is normally some part of it is missing. It's not because people don't want to share. It's just when you are doing the experiment, the habit is like I usually create a lot of notebooks, and I even myself have no idea which one is the final version. So yeah, it's kind of like you have to use some kind of software to help you organize and export everything to make the entire science community more organizable, and also how to faster onboard new people to the AI project, because most of the researchers are students and the research assistant. they only have like a very short time to work on one project. So if the onboarding process is too long, and probably when they are familiar with the whole process, they just, it's time to leave. So the onboarding process should be very short and easy to do. And also the most important question, why sharing the workflow is so hard? Because reusing the data is like just picking the apples from the trees and send it to the supermarket and get it consumed. That's easy because the apples, like the fruits and apples, are designed that way to do it. But reusing the workflow is like transplanting a tree. Like take the tree out from the soil and move it to another farm. That's what they are doing with the reusing workflow right here. It has so many hidden components you cannot easily reusable. There are the direct workflow code and steps, and some indirect is all this software and the OS dependencies. And most importantly, most of the workflow is actually relying on the data set existing in that environment, which is not existing in your laptop or any new environment, that's for sure. So reusing workflow is super hard. And what is the PyGeoWeaver? It's actually a Python wrapper of the GeoWeaver app, which was originally written in Java because I was super familiar with Java web application development back at that time. But right now, the Python is the main language, so we just create a wrapper. So now it's you don't have to interact with Java at all. You just use Python, and everything is still working. Yeah. So why should we start using PyGeoWeaver? Because there are so many libraries online that can do similar work. There are many benefits that other software doesn't have. It's like the package Ben just mentioned, the ML flow. You have to inherit its super class to use that. So it's you have to follow their rules to use ML flow. PyGeoWeaver is just bring on your own code, just directly using your code. It will always track the history and everything. That's will be easier if you are not that you don't have a very rich software engineering background. I have this code, I just want to make it use, and probably PyGeoWeaver is gonna be your choice. It has some user-friendly interface, drag and drop functionality. It's streamlined the sharing and the collaboration because everything you did in PyGeoWeaver it's gonna be a zip file. So you just share it around through the emails, through the Slack channels. It's super portable to share everything. Everybody got that zip file, got everything you did. So it will record everything you did so that no one's time is wasted. We found that a lot of people just click the run button, just some kind of try it out, testing the water. Actually, that time that is a very valuable experiences. And somebody see that history, they will know that in this scenario it will fail or it was success. So it records everybody's activities and share them together in one zip file. Yeah, I'm gonna skip some of those must-have benefits. It's portability, reproducibility, interoperability. How to make it easier to collaboration, automation, and scalability. I think it's easier to just show people how it works. And we also create a tutorial for the OpenScape cohort, I think 1 month ago. So it's in their cookbook. If you're interested, you can check it out. Okay, so yeah, this is actually the main component I want to talk about. If you have access to the slides or if you have access to the meeting notes, the link is right there. So if you click the second one, right here. Yeah, so this is GeoWeaver. Actually, where is the Python? The Python GeoWeaver is I actually started the PyGeoWeaver through a notebook here. So what you do is just pip install PyGeoweaver, and then import PyGeoweaver and PyGeoweaver start, and that's it. And once it's started, you can just go to this link, and here we go. So you basically can do everything here. It has a host. Host means that your computing resources. You can add any server, like a HPC, the EC2 instance here. We just using localhost. So localhost, if you click this button, all the password is eSIM. You can reset the password anytime by yourself. Yeah, it will search the entire server to find all those virtual environment of the Python. And right now it only has 2 because this instance is a brand new. I just set it up on the EC2 instance, like the West US West 2. This is the host, and then the process is like click this green button, and let's create one Python process. Let's see, test ESIB AI step 1, something like that. You can just make it up. And just write some random code. This is a very important AI component, but it's not actually. Just click, if you go down, just click add, and here we go. It will add a Python process here. If you click it and click the run button here, it will ask you which host you want to work on. You can actually choose a remote server to run the process, or you can choose a local host. Just click execute, and it will ask you which Python environment you want to use. I'm going to use this one. And just remember it, do not ask me again. The password is the same as the ESIP. Click remember password, confirm. And run again. Yeah, because it's too fast. It didn't capture that. Did you see that? So it just executed the process twice, and it gave me something like this. And this is the whole point of the PyGeoweaver. It records every run of your process. If you click this details, you will see its original source code and the output, like when it started, when it's ended, and the output. All right. So yeah, this is the first step, like how the PyGeoweaver is going to work on your laptop. And people say, okay, so you are talking about AI. So where is AI? This is not AI at all. I think this is actually the basic. If you want to do some AI work, you have to have this kind of tool ready, because as the time goes by, you do a lot of AI work, you will find that you forgot everything. We have seen that thing many times before. It's like 2 years later, you totally forgot everything you did right now. So running everything in GeoWeaver is like, this whole thing will be always there. And it's like this history will always be there. It will record it for you. And then you can export and share with anybody else when you want. So this is a basic, like a fundamental before you start an AI project. And actually starting an AI project is much simpler than you do. It's like, well, I would say I'm not doing it probably. I'm not saying that I'm doing it correctly, but this is what I do. It's like using AI to help you to build AI. So let's go to the ChatGPT and say, build a rainfall forecasting system using Python that can do the similar work as numerical models. Should be in one Python file. Now you can just let the AI to do the work. So this will help you to improve your productivity. Because if you want to start this, it's like it take a lot of thinking and back and forth searching. But this is like a starting point for you. It definitely make a lot of mistakes, but it's just a starting point. You can just copy the code, go to the GeoWeaver, paste it here, And that's it. Okay, so it has some like errors. No modules science can learn. Okay, so let's use PyTorch instead, because I just installed PyTorch. So what I'm saying is like this. I'm not saying I'm doing it correctly here because this is definitely controversial. It's like it gives you a possibility to do things. It's like it will save you a lot of time to like drafting any like dummy code to testing, just to prototyping. So prototyping step is like you can use ChatGPT to just overcome and they'll help you to get over that stage. And then you will dive into the specific steps and say, asking the specific questions. Let's just copy this code, go to the GeoWeaver, let's save it again. Yeah, I think this time it actually finished correctly. That's it. So it's like you can see that it trained the several epochs, and the next month's predicted rainfall is 85. This is definitely a dummy prediction, but it gives you a sense about how it works. So next step is like you can link a lot of steps like this into a workflow. That is what we're talking about, the pipeline. So workflow is like obviously this needs some PyTorch installation, but we cannot install that in the Python. So we install it in the shell script. So this shell script, it's using the virtual environment to install the PyTorch, probably Scikit-learn as well. Let's just install it together, and let's see if it works. It's the same. It just chose the local host and install all the package you need. Yeah, I'm not gonna wait until it finishes. I think it's already finished. Yeah, it does. So what I do is I want to link the two processes together. So I click this yellow button here, and I click this step I just created. So it's like depending on this process, depending on this process. So if I press Shift and then I drag from one process to another, I will create a collection. And then if I click Save button, it will ask you to input some pipeline. So that's like rainfall forecasting workflow. So forecast rainfall and save it. That's it. So right now I can just click this run button, and you can choose which host you want to run it on, and choose the Python environment. Just remember it, do not ask me again, it's annoying. Just click run button. Then just wait. Yeah, that's it. So the green means it's successfully executed. And if you click on the process, you will see the results. Actually, let's see this one. Yeah, it changed from 85 to 19 to 17.9 with no reason. This is like randomly forecasting. Although this is like a dummy ML model, but you will see this kind of stuff like happening all the time. So this is why you need tool like GeoWeaver to record everything. Because it's like, if you go to the history, you will find that this two process actually has the same source code, but the result is totally different. One is 85, the other is 17.9. So why? Why is that happening, right? So you need things to record the history, not the code history, but the code output history as well. This is why the PyGeoWeaver is so important. And also, actually, MLflow is doing the same thing, but it's totally a different way, at a different level. Actually, you can use MLflow inside the PyGeoWeaver as well. They are not conflicting with each other. Hope this makes sense. I don't know. Yeah, and last thing I want to demo is this download file. If you just click this download, It'll ask you if you want to export the workflow with code or history. This is recommended. Just confirm. Where is it? Oh, here we go. Yeah, need to enable the export. All right. So I just downloaded the zip file. It automatically unzip it, and you can see there is 3 items in the package. You can just zip it back to the zip file, compress, and share this zip file with anybody else. And let's say that this GeoWeaver is on the EC2 instance, right? I actually have a localhost GeoWeaver. Let's suppose this localhost GeoWeaver is your laptop. And then you can just go to the Weaver and import that package. You just download it. Start, upload. So what here is doing is like it importing all these history from your previous workflow and source code. Once it's finished importing, you will see everything the previous person have done, and including the code and the history and the output. So you can continue. Like even the environment is different, you just continue to do based on the previous person's work. And that previous person's work, including its failures and successes, not only success. Like Notebook, you can only see the successful story, but GeoWeaver, you will see a lot of errors, actually. Let me show you. Actually, this one is a production workflow. And its output is here. Its output is like predicting the ozone every day. And we have seen that ozone accuracy is much better than the original model output. Like the CMAC correlation is 17%, and the AI just boosted that into the 18%. We have seen this result almost every day. So it means AI is actually working. And this workflow is totally powered by the GeoWeaver. Oh, where is my GeoWeaver? I lost track of them. Yeah, this one. So if people share the workflow with you, you will see all the failures actually. Like the green ones are successful stories. I think there is some failures of this workflow. Oops. Yeah, something like this. So if you see something failed, actually that's an opportunity for you to learn something. If you click details, and you understand that this code will generate an error like this. It will says like 913. It has something with something wrong with this code. So it's like a learning history, a learning opportunity for you to do not repeat the errors as the previous person did. And this is also like how to make it better to communicate the knowledge among you among two teams actually. Either two teams or the team members within the same team. In the GMU, we have benefited from this software a lot. Okay, I think I'm gonna stop there. What about time?
31 now. Yeah, time is over, but if you have questions.
So I was curious about your comparison chart with other similar products. Is it appropriate? And if so, how would it fare against something like SageMaker?
It doesn't conflict with any existing software because it's at a very low level. It's actually just a platform for you to run some like shell script and Python code. So as long as anything you can run in Python, you can run it in the GeoWeaver.
I wonder, seems to me that SageMaker has an overlap with this. I was wondering how it would compare. You compared it with other products, but not SageMaker. So I was asking how it would compare on those criteria with SageMaker.
Yeah, it's actually not competing with SageMaker or any ML Studio sort of thing, because you can run your SageMaker experiment in PyGeoWeaver. Does that make sense? So it's like you can create a process to run SageMaker experiment, and then can just call SageMaker API here.
Okay.
So something like this. Yeah.
Is it possible to parameterize your scripts? Like if you want to change one variable?
Oh, yeah, that's a good question, actually. In GeoWeaver, every process actually doesn't have the external input parameters. All the changes are made inside the parameter. So yes, you can change any parameter you want for within the process. Excellent question.
I think you mentioned this earlier in the presentation, but how is this hosted and what's the storage size for? Because I see a lot of, like for example, the cold versions that and all the logs, error logs and all that.
Yeah, that's an excellent question. It totally depends on how long you worked on that workflow. We have worked on this workflow for 2 years, and this whole GeoWeaver package is about like 200 megabytes. So it's not that bad actually. You got 2 years of history, a lot of replication of code and output. It's 200 megabytes. It's not bad.
No more questions?
Awesome. Thank you so much.
Great. Thank you. Enjoy the rest of your day.